Degond. He's going to give us a talk on fluid models of swarming behavior.
Okay, thank you. Thanks to Jose and the organizers for the invitation. So I don't know, there was a stick, but somebody took it away. Oh yeah, sure. Okay, very good. I forgot my pointer. Okay, so I'm going to talk to discuss about swarming behavior. Actually, it's been a topic which has been discussed quite a lot during this meeting, and I think this is a sign that the topic is really emerging as a very important topic, and particularly that kinetic theory is a good or actually a relevant tool to look at swarming behavior. So I'm going to give us a small introduction about complex systems, which is about which exhibit this swarming behavior, and I will basically discuss two things. One is actually split in these two parts, and which has to do with the derivation of macroscopic models, and I would like to show that the derivation of macroscopic models for complex systems brings some new questions to kinetic theory that I think require the development of new concepts, and I will discuss a couple of these issues, one related to the lack of conservations, and the second one is related to the breakdown of the chaos property. And the reason to use macroscopic model is because to some extent they are well suited to the investigation of morphogenesis, and I will discuss about one aspect of this, which is how morphogenesis can be encoded into what's we have been actually discussing already in a couple of talks about the congestion constraint, the fact that there is a space exclusion when the particles have finite mass. Okay, so that's the idea. And okay, so we've been already discussing this along this workshop, so I will not spend too much time on that. Actually, for me and for many authors, I think this is a definition which is slowly converging, that a complex system is a system where you have a large number of interacting agents. Most of the time, these interactions are local, which means that the agents do not have complete information about the state of the system, but only have local information. We've seen that about the Cooker-Smale model yesterday, which was discussed by Eitan. And sometimes there might be global interactions. If you think of finance, where information on the news are accessible to everybody, but some information is private. So some information may be local and some information may be global. The other aspect of these systems is that they generally have no leaders, so there is no big architect of the whole structure. And in spite of that, they exhibit large-scale emergent structures. So that's called now emergence, where the large-scale organization sort of emerges spontaneously from the behavior of the agents. Okay, so here are a certain number of examples. Actually, this is car traffic. You have a succession of empty road and congested parts, and with a very sharp actually boundary between the congestions and the uncongested parts. And you have all experienced this on the freeway. All of a sudden you're blocked and you don't know why, and all of a sudden then it starts again and there is no reason for that. And these kind of stop and go ways are a typical example of an emergent structure, which emerges only because of the local interactions and the rules of interactions between the agents, the cars. Here is this picture. Is a little bit small. Is a milling structure in the school of fish. Here you can see that the size of the mill is about a few meters, 10 meters, and while the size of the individual is a few tens of centimeters, and the area they can perceive is also very, very limited. And so clearly this very nice structure is an emergent structure in the sense that no individual has the project of, doesn't say any, there's no fish which says, hey guy, why don't we start to turn around? And the other saying, well, it's a good idea, let's do that. So okay, so maybe there is a question also which is more a biological question of the functions of this structure. Why does the system has been built in such a way that this kind of structure appears, and what kind of functionality it has, what kind of optimization does it reach? Maybe some kind of better protection against predators, maybe a better organization in case of an attack or something like that. This is a herd of a sheep. Actually, you've seen the movie in the talk by Aronson. This movie was shot by my collaborator Terola in the Alps, in the Mercantour Park. And there is actually a point here that you might not see. This is a dog, and the dog actually in the movie, I will not show you the movie because of lack of time, but the dog basically spins around the herd. The herd is moving this direction, and there is very nice droplet structure that emerges actually probably due to the fact that, okay, the sheep want to escape the dog, but on the other hand, there is this exclusion constraint which builds up this very nice and compact structure. This picture is about robot swarms. This is a very hot topic in robotics, that trying to build systems of locally interacting robots or whatever systems where the functionalities are encoded very simply as rules between the agents. So typically with these kind of things you can solve problems such as finding an optimal path or things like that. Okay, in particular my biology colleague has also worked on these kind of things, and by using optical pheromones has reproduced the behavior of ants. So these Bayer-inspired algorithms and systems is a very quite hot topic in robotics. Okay, so in describing these complex systems, I would say the typical models that are used are so-called agent-based or individual-based models, that are models which try to reproduce the behavior of each agent and of its interactions. In kinetic theory, we would call that particle models. So this is nothing else than particle models. And they are really overwhelming, but you can find in the literature small fractions of work devoted to macroscopic modeling of these systems. And again, in this small amount of literature devoted to macroscopic model, there is only a very small fraction of these models which really are based on say kind of rigorous approach going from the particle system to the macroscopic model. Most of the macroscopic models are built out of phenomenological considerations that you want something that has such and such and such behavior, so why don't we try to put this and this and this term in the model, okay? And of course there is nothing against this procedure, but there are some reasons why you would like to have some more rigorous link between the microscopic and macroscopic scales, and that has to do with the data analysis of the experiments, because current experimental facilities actually are booming, and you have now experiments. I will show you some pictures of experiments that produces a extremely large set of data, up to a point that is very difficult. Traditional statistical methods, are very, have have trouble to find out what are the relevant things to look at. So if you think of a principal component analysis, this will produce you some, in a very large set of dimensional space, it will produce you a manifold where, you know, but the manifold it will be hard to connect this to anything that has, you know, a meaning in terms of, and what you want to gain out of this is, after all, an understanding of what's going on. So in fact, there is the other idea is that the interactions between the elementary interactions between the agents is very complex. It's not so simple as, you know, d1 over squared r squared law of Coulomb for two charged particles. So the traditional idea of physics, which methodology, which is to start from the simple and to go to the complex, supposes that the simple is easy to understand. In this case, if you think of pedestrians or whatever bacteria or things like that, these simple interactions between small systems are not easy to understand. And not only that, but also the insight that you gain on looking at you know, two particles is probably irrelevant for the large system, okay? Because in fact, you don't have a simple, say, combination of the interactions like just a summation of binary interactions. So whatever insight you can gain from an experiment with two, three, say 5 fish will be probably irrelevant to study the entire school. And so in doing the experiments, you have to record the entire system, sort of track the behavior of each agent over time, and out of this huge set of data, try to get some insight. And in this case, the macroscopic model might be a very interesting intermediate step because it allows you to look at global data, global behavior, allows you to sort of, gain insight. And once you have this knowledge, then it might be interesting to go back to the individual based model and try to extract the parameters that are relevant for your individual based model out of the understanding of the or out of the matching of the macroscopic model with the data. Okay, but for this you need really to establish a sort of reliable connection between the say microscopic scale and the macroscopic scale. Okay, okay, so continuum approaches are, I think, important in this system. Okay, these ideas are not, okay, it might, I mean, I'm sure you're there in this community, I have no trouble to advocate this point, but there is, in other communities, it is quite hard. I remember I talked to Vikshek once, and he said, well, why don't you bother with PDEs, because nature is discrete, and so PDEs are irrelevant for this, okay? So there is this idea that macroscopic models are irrelevant, and so it's not always completely obvious that this can be an interesting thing to do. Advantages of continuum approaches are numerically, the numerical cost is independent of system size. You encode the size of the system into the number density. This is just a number. Agent-based models have a cost which blows up like at least a polynomial of the system of the number of particles. Okay. The other thing is that morphoanalysis on macroscopic system is sometimes easier because discrete systems are very delicate to analyze. And you think of networks, for instance. I've been attending a conference on networks last week in SAMC in North Carolina. It was a lot about statistics of networks, and I realized that there is up to now no really adequate descriptors of networks. You can think of degree distribution or of things like that, but it's still very rough to understand, how for instance, to see the difference between two very different networks, but which might actually have the same degree distribution, for instance. So morphoanalysis of discrete system is rather complicated, and sometimes it's much more easy to encode it at the level of the macroscopic model. Okay. So what are the associated mathematical questions? Okay, so in linking the agent scale to the macroscopic scale, actually, some of the classical kinetic theory tools are inadequate. And the reason for that is that there are a certain number of things that break down, such as, for instance, conservation properties. Then usually, your particles do not obey any conservation law. You're lucky if you have mass conservation. It's even not true with cells which divide. A lot of the derivation of the macroscopic models in kinetic theory relies as a cornerstone on the conservation laws. Okay, so what to do when you do not have this? This is one question. The other question is has related to the buildup of correlations. Okay, you have self-organization systems that bring order. So the entropy, in some sense, goes the other way as normally. Okay. So, but in this case, it might be that because you build up correlation, then your macroscopic description, which relies mostly on the fact that your system of particles is nearly statistically independent, then your macroscopic description is maybe inaccurate. There are examples, and I produce one, where actually it can be shown it's wrong. Okay, so there is actually the need for going beyond the chaos property in order to build kinetic and fluid models for complex systems. I will also touch upon encoding morphogenesis into macroscopic models and my point is that it is easy to do that by unilateral constraints like if you think of the congestion or exclusion constraints like in the case of the herd of sheep. And that actually produces phase transition. You can view this as okay, so there are no sheep around, but sometimes you have a scattered sheep around, and then you have the group, and so you may view the flow of sheep around as a compressible phase, and this is an incompressible phase, like in traffic. Traffic jam is an incompressible phase, and the free traffic can be viewed as a compressible phase. And the transition between the phase transition when you reach the border of the congestion is really a transition from compressible to incompressible fluid dynamics through the saturation of this constraint. So I think there are a lot of problems, interesting mathematical problems related to these questions. Okay, so this is the kind of question I would like to briefly discuss. As far as the applications go, my interest is in this collaboration with this biologist in Toulouse who's working on social interactions in animal and actually human or also robot societies. Here is a picture of an experiment we've been conducting in the city of Rennes, where we have used motion capture technology like the one you use when you want to in the movie industry when you want to paste an actor playing in a room which is with basically a blue background and nothing around with a background made of synthetic images. And so there are some you have some captors and then you have some infrared cameras. You can do triangulation to record the coordinates of the captors, and then you can reconstruct the trajectories of the agents. Here is an experiment where the people move in a circular annulus arena, and of course then the problem is of course from the knowledge of all these trajectories to say something meaningful about what the agents are doing. This is an experiment which is not very clear about fish schools. These are experiments about herding. We're also working currently on ant trail formation and also on the ant nest construction. And the problem of the building of insect nests is really an emergent phenomena, because you can think that it's really a product of all the interactions between the insects and their ability to you know, to paste a piece of mud here or to remove a piece of mud there. The whole structure is a quasi-static structure. It always changes over time, but the general structure remains the same. Yeah, okay, so these are the things that we are interested in, okay? Okay, so let me go to the first topic, which is this linking of the agent scale and macroscopic scale. So as I said, classical kinetic theory, and let's think of the derivation of Euler equation from Boltzmann equation, heavily relies on local conservations. Here I have an artist view of a collision between two particles. By the way, this is the cover page of this journal, Kinetic and Related Models, and you are welcome to send, and which I've been starting with Tong Yang and Seiji Ukai, and so now we're in ending the third year, and you're welcome to send us manuscript. I think the journal is doing pretty well, and we have a lot of very good papers and a lot of nice people in the editorial board that are doing a fantastic job. Okay, so that was just, you know, this advertisement section. Okay, so it's just about the half of the talk, so it's just the time. So back to our normal program. So this is a picture of the artist view of a collision of two molecules, two hard spheres, according to you know, Boltzmann picture. And in this collision, there you have preservation of momentum and energy. These conservations are crucial for the establishment of the macroscopic models. Unfortunately, in a complex system, this is never true. So you have to go beyond conservation properties. Okay, and it's such to a point that you know, the theory of really of hyperbolic systems has expanded out of the theory of conservation laws. And conservation was really the key word. And here we have to go really to bypass this conservation concept. So for swarming self-propelled particles, there is no momentum conservations, and so the derivation for the derivation in the case of the Vic-Sheck model I'm going to present, we were successful in finding some extension of this conservation concept, which enabled us to derive the model. I think that this kind of idea is really crucial to for the future of this field. So in the case of the Vic-Sheck model, that's actually a model which has been proposed by Vic-Sheck in PRN 95. Actually, it's a model. There's the original model is a three-zone model. You have a repulsion region where the agents are close, an attraction region where the agents are far away, and they have a alignment region where in the intermediate region. And that three-zone region is actually originally not a model proposed by Cousin, as Eitan said yesterday, but originally proposed by a Japanese guy named Aoki, but not our Aoki. Okay, so it's another one who was working in the fisheries of some agency related to fisheries in Japan, and he first proposed this three-zone model, out of which Vic-Sheck extracted the central, the intermediate part, and focused on the alignment interaction. So here, particles, so you mimic, you know, the self-propulsion of the particles by saying that they have constant velocity and that they try to align with their neighbors. And in our derivation of the